Okay, cool, this works. Welcome everybody to this morning's session, which is on a very important topic, bridges. We've seen recent hacks, so there's definitely work to be done in both theory and translating theory into application. My name is Joachim. I'm a PhD student here at Stanford. I work on consensus protocols, specifically proof-of-stake Ethereum security. And I'll be the session chair for this session. And I'm very happy to introduce our first speaker of the session, Patrick McCrory, who is with Infura, and he'll be talking about validating bridges as a scaling solution for cryptocurrencies.
Hi, everyone. Oh, I do have the Wi-Fi. Cool. Thank you for the introduction. So today I'm going to talk about validating bridges, which is basically rollups. Who's heard of rollups before? Cool. Who understands how they work? Okay, that's like half, sort of exactly. So the motivation for this paper was sort of last summer. I was just sitting at home. I got the sort of COVID, we're all in lockdown, and I was getting really annoyed that no one had wrote this paper yet, just to really explain in basic terms what rollups are trying to achieve and what they're trying to build. So that's sort of the motivation for this talk. And so without further ado, let's just get started. So as you can imagine, under the hood of a rollup is just a bridge. And what we've really been doing for the past 10 years is bridge engineering. So it's building bridges that hold assets. So the classic example is Coinbase. I lock my funds into their bridge. It gets unlocked in their service. I can transact as much as I want. Then eventually I withdraw my funds and I take it out of Coinbase. And you can imagine, the Coinbase bridge has some functionality. It could have a deposit function, a withdrawal function, and an allowance function. When I want to withdraw my funds, I'll ping Coinbase to say, Coinbase, let me withdraw my 1,000 ETH because I'm a wonderful whale. And then Coinbase will send to the contract to say, contract, allow Alice to withdraw her 1,000 ETH. Now, from the perspective of the bridge, because that's the most important thing, that's the biggest takeaway, we're always considering it from the perspective of the bridge. The bridge has to, be convinced that Alice is entitled to this 1,000 ETH. The bridge has all the assets. The bridge has to protect these assets. And in this case, the bridge is just trusting Coinbase. If Coinbase has authorized a 1,000 ETH withdrawal, then that's pretty much saying that this off-chain database is safe, is well, is alive, and Alice is entitled to these funds. So then Alice can come along, withdraw the funds out of the bridge, and obviously escape. But generically, what's happening here? What's sort of the interaction, what's happening? Generically speaking, we have this bridge contract that holds all of the assets. And this could be billions of dollars. And then we have this off-chain database with the account balances, the program state, and the off-chain database is really just describing the liabilities. And from the bridge's perspective, the bridge wants to be convinced that its assets will cover its liabilities on this off-chain database. And the trust assumptions really, how is the bridge convinced that the database is okay and it can cover these liabilities? And over the years, this trust assumption has evolved. So obviously 10 years ago, the easiest way to build a bridge was with a single authority, the one ring to rule them all if you're a Lord of the Rings fan. There's the Coinbases and the Bitstamps. Then we sort of started moving on towards these multi-authority bridges. So as long as K out of N validators agree, then you can withdraw your funds from the system. So there's like the RSK, the Liquid, and in fact, many bridges now that exist on Ethereum, so I need to update those logos. And then further on, we moved on to these crypto-economic bridges. And Polygon's a great example of this with their proof-of-stake bridge. The real difference between these crypto-economic bridges and the multi-authority bridge is really, sort of skin in the game. And the multi-authority bridge, they're all pre-installed. They're sort of appointed in advance. For a crypto-economic bridge, I have to put my skin in the game. I put down my funds, and I declare I'm going to protect the system, because if I don't, I'll lose my stake. But even with these crypto-economic bridges, they're basically just multi-authority. So back in 2021, around 6 entities controlled 85% of the stake on Polygon. If they all collude, they can steal the funds. But at the same time, if they all work together, they can protect the funds in the bridge. But what's really annoying is that in all of these systems, we're trusting less than 10 parties to protect our funds. And this sucks, right? The whole point of Bitcoin was, to remove these trusted intermediaries that make the system work. And now we've just reintroduced these intermediaries when we want to do some fun interaction. And it sucks. And it doesn't just suck from an ideological perspective. It sucks from a practical perspective because they keep getting hacked. Mt. Gox lost 850,000 Bitcoin that represents 6% of all Bitcoin that will ever exist. Bitfinex lost 120,000 Bitcoin, although if anyone's aware, Bitfinex did get back 97,000 Bitcoin by the Instagram wrapper. Don't know if anyone followed that wonderful tale. But the main point to take away here is, these services don't want to get hacked. They want to provide a useful service to their customers. But the issue is that they have to take a set of human processes to protect a single signing key. And the issue is that humans don't scale. So every time I create a new service, I take these human processes and try to reapply it here. And that's just difficult to do, so they lose their funds. And Taylor has this wonderful spreadsheet I can share afterwards. She's kept track of all the hacks for the past 7 years. So it's a great document to reinforce this point. What about these multi-authority bridges? Surely, what's nice about a multi-authority bridge is that it makes it a bit harder. Instead of compromising one entity, you may have to compromise 5 validators out of 9. But again, that's not impossible, and the run-on bridge was a great example. They lost $500 million worth of crypto. But actually, it's 4 of these validators were actually just one company. Then this one company had pseudo mode over the other validator, so really only one entity was hacked. So it wasn't really a multi-authority bridge, but it's a great example of security by obfuscation. But the main point here is that we've sort of forgot about this motto, not your keys, not your coins. It's sort of a Bitcoin maxi motto. But we forgot about it when we're building these third-party services or these off-chain services. So the question is, can we transact on an off-chain system like Coinbase while maintaining self-custody of our funds? So I can lock my funds into the service, and then I can transact on the service. But I never have to trust the off-chain system to protect my funds. That's sort of the goal for these bridges, the ultimate goal. And this goal started back in 2014 with the original sidechain paper. They call it a two-way peg. They don't use the word bridge, but actually what they're trying to build is this trustless bridge. And the idea is very straightforward. I take my Bitcoin, I lock it up on the Bitcoin network, I then unlock it on an experimental blockchain, I transact here as much as I want, and eventually I can move my funds back to Bitcoin. And that was the goal of the original sidechain paper. Of course, Bitcoin couldn't support it, so it can never be built. That's a dilemma, but anyway, that was the goal. And it's a brilliant goal, it's a very, very exciting goal that we wanted to achieve. Today, if you're going to reclassify this, I would call it the consensus bridge. The idea is that there's this other experimental blockchain with its own consensus protocol. Then on the bridge that may sit on Ethereum, the bridge is just really checking, any decision made by that consensus protocol. So the classic examples like proof of work. Maybe on the Bitcoin, there's a new block. You take that block header with the proof of work, you send it to the bridge on Ethereum. Ethereum will check the proof of work and say, yep, it's a valid block, and then process it. But the issue here is that if you're relying on an external consensus protocol to protect the funds in the bridge, then actually you're still trusting a set of parties. So the classic example here is that in proof of work, a miner could produce an invalid block for Bitcoin, but then take that block header and just send it to the bridge on Ethereum. The bridge doesn't check the integrity of the block, it just checks if the proof of work was valid. So you have two issues, it's still trusted. If the consensus protocol goes offline for whatever reason, your funds get stuck on this experimental system. And that sucks. And obviously, if you don't have fancy zero-knowledge proofs, then there's also the integrity issue as well. An invalid transaction could be processed by the bridge. And this is sort of how the Rainbow Bridge works between Near and Ethereum today. So again, the question, can we really build a bridge that protects us from an all-powerful adversary? So even if the entire system goes offline, I can still get my funds out. And this all began with Plasma. On hindsight, this all began with Plasma. And Plasma was this idea of building a bridge that can validate independently that everything's OK. Now, in classic, I actually said this to Joseph yesterday as a joke, in classic Poon style, the paper is very, very interesting to read. It's great paper, great insight. It's just very difficult to read. But over the next 2 years after they proposed this idea called Plasma, we had 2 years of people in the community proposing different variants of Plasma, trying to find one design that will work and obviously save the day and build the best bridge. But Plasma never achieved its goal. Plasma was just way too complicated of a design space. And thanks to a wonderful guy called Barry Whitehat, who was around the past 2 days as well, if you can catch him, he's ginger, he's Irish, wonderful guy. He actually simplified the entire design space. He basically said, well, let's take the data and just post it to Ethereum so we don't care about the data availability problem anymore. We just care about state transition integrity, which we'll explain later on. So he posted this repo, simplified the entire space, and it was called a roll-up. And that's where roll-ups come from. That's sort of initiated the next wave of solutions that were built. And I would call this a validating bridge. Because the idea is that you have this executor, for example, they're going to update the database with my wonderful 1990 animation. They'll then take their proposed update, and they'll send this to the bridge. And they'll say, bridge, this is the new state of the database. Now, the bridge will step back a bit and say, well, executor, I'm not going to trust you. I'm not going to blindly trust your signature. You have to somehow convince me that this proposed update to the database is valid and correct. And so then the executor will have to send some convincing evidence to the bridge and say, yep, here's convincing evidence that it actually is a valid update. The bridge will check this, is it safe, is it alive, and then it will accept it. So it's validating everything about the off-chain system. And this is basically what the roll-ups are trying to build. They're all trying to build this validating bridge under the hood. And hopefully, if one team can get it right, then ultimately, the bridge is protecting you, the smart contract is protecting you, and a system like Ethereum is protecting your funds. So it's a bit like a box, sort of punching the adversary and not letting the adversary to win. Well, this sounds really cool. But it also sounds a bit too good to be true. So how do they work? So we're briefly going to go over, here are the agents, a high-level overview of how validating bridge may work, and of course, the threat model and the security properties. What does it mean to be secure in this context? So the agents are very straightforward. We have Alice. She's an honest user. She wants to interact with her mooncats. She just wants to interact and send transactions. We have the sequencer. The sequencer's role is to take all the transactions, order them for execution, and then pass them on. Then the executor will take the ordered transactions, execute them, and propose an update to the database. So let's have a high-level overview of how this works. And of course, all roll-ups are different in terms of implementation, but this is just a high level. So Alice comes along, and Alice will deposit 1 coin into the bridge. Then eventually, this will pop up on the off-chain database. Then Bob comes along, hi, Bob. And Alice wants to send 1 coin to Bob. So Alice will sign a transaction, give it to the sequencer, and that's it. Then the sequencer could notify Bob to say, Bob, you're going to receive 1 coin. But the transaction's not yet final. It's not even publicly known. It's just pending. The sequencer will wait around for a while, collect all the off-chain transactions. And eventually, the sequencer will order the transactions for execution and submit it to the bridge. And the bridge will have this list of transactions, and it will decide, this is the order they should be executed. Then later on, they're ordered, but they're not yet executed. An executor comes along, he'll pick up the transactions from the bridge, execute them, and then propose an update to the bridge to say, bridge, given those transactions, this is what the database should look like. And obviously, the convincing evidence is sent as well. And this just happens continuously. We order transactions, we execute transactions, we order transactions, and the bridge is always checking that it's valid. And of course, any honest user should be able to come along, take the data from the bridge, recompute the database independently, and then of course check that the database is correct, and may use that for other purposes. So that's how it works at a high level. So what's the adversarial threat model? Who are we trying to fight against? Or who's trying to break the system, should I say? So there's two ways to think about it. One is message flow control. The only guarantee we have is that Alice can send a transaction to the bridge in the layer 1. Any message sent on the layer 2 system could be viewed, reordered, or dropped by the adversary. The adversary can control the entire off-chain system and guarantee no message is delivered. And 2, we assume the adversary can corrupt nearly every single party. The only person who can't be corrupted is one honest party, which could be the Mooncat user, and of course the bridge on Ethereum. All sequencers and nearly every single executor could be corrupted. And this is really the most powerful adversary you can describe. And in practice, many of the rollups cannot defeat or constrain this beast. It's a very, very difficult adversary. So what does it mean to be secure in this context? What are the security properties? What are the goal? So the ultimate goal is to protect the safety and the liveness of this off-chain database. And there's 3 sub-goals to this. 1, remember, this is all from the perspective of the bridge. The bridge needs to be convinced that all the data is publicly available, so anyone can compute a copy of the database. 2, the bridge needs to be convinced that every transaction processed by this database is valid and correct. And 3, the bridge needs to be able to enforce such that if the entire system eventually goes offline, one honest party can eventually get their transactions executed by the system. Now, the important bit is the bridge has the sole discretion over this entire system. There's no honest majority. There's not even a peer-to-peer network. It's just from the bridge. So what about the data availability problem? How does that work? Or what's the problem there? So there's 3 questions. Why does the data need to be publicly available? What data needs to be publicly available? And how do we guarantee it's publicly available? So why does it need to be publicly available? Well, it's because we need one honest party to assist the bridge. They must have a copy of the database in order to execute transactions and propose an update. If only the adversary has a copy of the latest database, then no one can propose an update to the database. Very straightforward. What type of data can be posted? So there's 2 types of data. Typically, in the optimistic rollups, they'll send a list of transactions to the bridge. So everyone can see every transaction that's executed. With the validity rollups, what's quite quirky is that they don't have to send the transaction data. They'll send the validity proof alongside a state diff. And basically, a state diff says this is how you update your database. You replace these storage values. And so in a validity rollup, you don't have to reveal the transactions at all. So it's their side effects or their impact on the database. And that's really exciting. And how do we guarantee it's available? Plasma tried to do an on-chain challenge, and obviously that failed. Some teams are now relying on data availability committees, where you have 10 parties. You assume one is honest, and they'll all sign off that the data is available. And of course, rollups, they just take the data, and they send it directly to the bridge. And that's how we guarantee it's available, because it was posted to Ethereum at one point in time. So what about the state transition integrity problem? How do we solve that? Well, the problem is that if the adversary could include one invalid transaction and get it processed, they can steal all the funds in the system. So that's the problem we're trying to solve. And the way we solve it is, bingo, sort of the optimistic versus the ZK, the fraud proofs versus the validity proofs. This is actually the one topic that everyone talks about, but there's only one problem in the space. And so I won't go into detail here, because obviously there's not much time. But that's what, when you hear fraud proofs or validity proofs, they're trying to solve this one problem. And of course, what's really exciting is that, if I send a proof to Ethereum, the proof does, or even just the fraud proofs, all these off-chain rollups, like the Arbitrums, Optimisms, ZK Syncs, They all have these quirky virtual machines that are, that may or may not be compatible with Ethereum, like Caro. Caro has absolutely nothing to do with the EVM, yet Ethereum can check that it's valid. So now we can build these cool experimental blockchains and prove that they're valid to Ethereum. What about censorship resistance? So I won't go into the detail here, but the problem is very straightforward. Alice will ask the sequencer, can you process my transaction? And the sequencer says no. You have to deal with customer support before you get your funds out. So what I do want to highlight is that the sequencer has absolutely nothing to do with censorship resistance whatsoever. The sequencer could be fully centralized, and you can still have a censorship-resistant system. You just have to assume there's one honest executor out there who will pick up the honest user's transaction. So there's one honest party assumption there. And there's two approaches for it. So in the V1 rollups, they had this on-chain exodus. So if a transaction was censored, the database would be frozen, and then everyone could withdraw their funds. In the V2 rollups, they focused on forced inclusion. What I mean by that is any user can send a transaction to the bridge, and the guarantee is that the system can never freeze or go offline. It must always eventually make progress. But there's a lot of nitty-gritty details here that aren't well explored. So if you're interested in writing a paper or doing research, this is the first thing I would tell people to go look at. There's race conditions, delay attacks, overhead of constraints. Any paper that even tried to summarize this would find so many jewels of why it's a non-trivial problem. But if you can solve all three problems, then hopefully you can slay the beast and deploy a secure layer 2 system. And also for the OGs, this is the bear wheel from 2014. So this is the old bear market. And obviously we're slaying the bear wheel. But other problems emerge, and obviously I don't have a lot of time for this talk, but I'll summarize them. One is, what happens when you have 100 different rollups? The assets get fragmented between the rollups. So if I'm an Arbitrum, how can I quickly get my funds the optimism? Or in fact, another cool idea is, what if I'm on Arbitrum? Maybe I want to go to Optimism, take a loan on Aave, or Aave, take a loan on Aave. Maybe go to Starknet, perform a swap, and then bring the funds back to the Arbitrum. How can we gracefully handle failures when there's smart contract interaction along the route? It's very much a Lightning Network problem with HTLCs, et cetera. It's a very fun problem that not many people have really solved. Another is the return of the data availability challenge. The biggest cost for rollups today is data. Could we optimistically keep the data off-chain, but obviously post it to Ethereum in the worst case? The problem there is the fisherman's problem, which we can talk about afterwards, but I think it's very solvable today. What's really cool is these experimental virtual machines. We have Caro, we have these EVM equivalent virtual machines, compatible EVM, or even EVM native now. And it's just really cool to see that you can build these experimental virtual machines in layer 2, experiment with new features, but still get security from Ethereum. I've already spoke about censorship resistance being non-trivial. MEV is obviously a big problem. The sequencer is the only party with the list of pending transactions. They hold on to these transactions for 10 minutes, 1 hour. They can extract as much MEV as they want. And finally, just this formal model. How do we evaluate the ideal bridge? So in the end, is it worth it? Should we care about the rollups? So I'm going to just one minute. Awesome. So it's worth it because we're now moving to the world of Web 3. When you consider the Web 2 world that we've had for the past 10 years, you lock your funds in Coinbase, and you give away full custody of your funds to Coinbase. Today, if you lock your funds in Arbitrum, you lock them in, but you still maintain custody. But you still get this wonderful Web 2 experience of sort of instant finality, or at least it feels that way when you interact with it, thanks to the sequencer. And so I hope in the next 5 years, when we see these rollups emerge, it will feel like you're interacting with Coinbase or Binance, but actually behind the hood, there's a centralized sequencer, but a decentralized backend that's guaranteeing that your funds are safe. And so the reason why this is going to be useful is because custody is going to be a liability for a lot of companies. So my final slide, as we saw over the past 10 years, it's difficult to build a centralized service to hold cryptocurrencies. Coinbase has $100 billion worth of crypto today under custody. It's very difficult to compete with Coinbase because I have to take a set of human processes and try to protect $100 billion. And I definitely do not want that liability in my life. They keep getting hacked. So if one rollup team can get it right, if they can build a validating bridge that actually works, then what's really exciting is that any operator could take that code, a bit like Linux, you take the code, reinstantiate it, and offer your service out to your users without taking custody of of the funds. So I don't think users care about this at all. Users just want to play with their Mooncats. Operators care. Operators can offer the same service as Coinbase without having to protect $100 billion. And that's why I think this will take off. So thank you very much, guys. Cool. Any questions?
We have the mic. Thank you. Thanks, Patrick. You're testing my session chair.
I know, I saw it. I saw you come up,
Folks
and I was
can
like,
line
ooh.
up at the mic. There's already one question. Go ahead.
Doesn't work. Oh, here we go. Thanks for the talk. I wanted to ask you by kind of targeting these validating bridges, you kind of do away with L1 to L1 bridging that are traditional, what we call bridges. So if you kind of roll this forward, do you kind of expect a future where there's one giant winner blockchain, say Ethereum, and then the other L1 chains become sort of L2 chains on top of that one so that everything can be validated? If I kind of roll this forward, that's kind of what I imagine. I just want to get your thoughts on it.
So I don't want to say that L2s will replace L1s that exist today, like Ava, for example. I don't think Ava's going to go away because of the L2 world. I think that if you want to build a centralized looking service, you want to build an L2 because you'll get this nice instant finality. But if you want to build an L1 network, then sure, you'll just deploy an L1 network. I mean, it just comes down to trust assumptions. Do you want to trust an honest majority in a new network, or do you want to have shared security from a network like Ethereum or another layer 1? So I think those is both running next to each other. But I think one thing I do want to highlight is that the bridge between L1 and L1, I don't typically like calling those bridges. I just call them a synchrony solution. You have these man in the middle who synchronizes an update between two databases. So it's like an interruptibility solution, which is also quite nice. So I hope that answered it. Cool.
So thanks, Patrick, for the fantastic talk. So one aspect I was missing, maybe, was the privacy aspect. So if I understood correctly, it seems like, for example, what you call the executor could see pretty much who pays to whom, how much, what time. So is there any work or any thoughts on privacy, and what's your thoughts about that?
So right now, obviously, all of the rollups have zero privacy in them. So even for the validity systems like Starkware, they use zero knowledge. Well, they don't actually use zero knowledge proofs, but they use for the integrity, not for the privacy. But because you can build arbitrary experimental virtual machines, and all Ethereum's eventually going to get is a proof, then actually your virtual machine here could also be private. There's no reason why you can't deploy a private contract in these systems. And then you get some privacy from the operator. There's also some of these protocols, like the fair ordering protocols, where you could do a commit and reveal there as well, or threshold decryption, so they aren't aware of your transaction before it's ordered. So yeah, you can definitely build a privacy system on this.
Perfect, thanks.
Cool.
We have time for one more question.
Oh.
Okay.
Yeah, so here we're referring bridges as custody solutions, and then you're talking about layer 2 as those type of rollup bridges. So how would you categorize layer 3, layer 4 if they ever comes? Will those be bridges of bridges?
Yeah, I think so, yeah. So I think this is sort of the Starknet dream, isn't it? So you'll have the Ethereum network, you'll have a bridge that's Starknet, then you have these opchains. And so what will happen is that you'll lock your funds in the one opchain, and then, what you could do in this network is move your funds via the bridge, the layer 3 bridge in this sense, from opchain to opchain. But all that will be composable. And basically, from the user perspective, all that gets aggregated into a single update. So as a user, you'll just say, move it to this opchain, then within the next epoch or the next update, it'll be moved across. So I think from the user perspective, they won't be aware of the bridges for the opchains, but there should be a bridge contract there. So you'll see layers, a hierarchy of bridges in a sense.
Got it, thank you.
Cool.
Cool. Let's thank Patrick one more time.
Awesome.